Hi, this is the first part of the presentation on hypersonic flow. I'll just give you a starting flavor and then we'll have more detailed presentations later. Let me change this to display mode. Okay, so my name is HK Narahari or Narahari K. Hunsur. I'm a retired professor from the Ramaya Institute of Applied Sciences. Most of the material here is from the published sources. Copyright of all authors are hereby gratefully acknowledged. Some of these videos are also in the GitHub link I have shown here. So presentation overview, what is a hypersonic flow definition? Why should we study it? Because they are used applicable to missiles, launch vehicles, re-entry bodies. What are the key challenges? Some of which I'll talk about in this presentation. Later presentations will cover the other things. Key challenges being high temperature effect, low density flow, reacting flow, shocks and entropy, and fluid dynamic and CFD issues. Hypersonic vehicles are pretty commonplace. There are many more of them than supersonic aircraft, for example. Missiles, ballistic variety, which go out of the atmosphere and come down, re-enter the atmosphere. Launch vehicles and also re-entry bodies, like the ones which take the astronauts outside the space and come back. All of them undergo hypersonic flow conditions or subjected to that. There is no simple definition of a hypersonic domain. Mach numbers at which supersonic linear theory fails is one such definition, approximation. Another approximation is where gamma, or the ratio of specific heat, is no longer constant, and we must consider temperature effects on fluid properties is another definition. In some cases, if it's a blunt body, any Mach number greater than 3 causing large disturbances to the flow is to be considered hypersonic conditions. And Mach number greater than 5 might be a starting point for more highly streamlined bodies. So the major issue is the thermal barrier, what is called a thermal barrier. Earlier, you have heard of sound barrier. Initially, in the aeronautics, they thought nobody could fly faster than the speed of sound, but that was broken. Thermal barrier is not something you can break. The key challenge in thermal hypersonic aerodynamics is to find a way in estimating the surface temperature of the body. Typically, a re-entry body enters the atmosphere from space at about 11 kilometers per second, give or take a little, causing a huge bow shock. Estimated temperature behind that shock would be around 11,000 degrees Kelvin. Just to give you an idea of what 11,000 degrees Kelvin means, the estimated surface temperature of Sun is around 5,000 to 6,000 degrees Kelvin. Internal temperature of Sun is much more, of course, and the outside temperature is also higher, but the surface temperature is estimated about 5,000 to 6,000 degrees Kelvin. At such high temperatures, internal energy goes into different modes: translation, vibration, and rotation of air molecules, ionization, radiation, dissociation, meaning that O2 becomes O, N2 becomes N, and all that kind of thing. Classical methods developed for supersonic flow will, of course, fail. Just give an example. At 78 kilometers altitude, temperature is around 197 degrees Kelvin at an entry velocity of 9 kilometers per second, which is equivalent to Mach 32 at that temperature and altitude. Classical equation of perfect gas is the following equation. The T naught will be T infinity, which is the 197 degrees Kelvin, into 1 plus gamma minus 2 by into m infinity square. This gives you a temperature of 40,000 degrees Kelvin, of course, which is not very meaningful. Why is this? What happens here is several issues make this prediction wrong. O2 and N2 start dissociating, absorbing a lot of energy. Breaking O2 into O is an endothermic reaction. Similarly, for N2, it's an endothermic reaction. A lot of energy is consumed by them when they dissociate. And also, gamma is no longer 1.4 as we normally use in atmospheric conditions. Chemical reactions soak up energy, reducing temperature. Real gas effects to have a role to play. So all of them together ensure that this theory, this estimation, is badly off. Another example, a simulation at Mach 16 and altitude of 40 kilometers predicts a shock wave so energetic that the translational, rotational, and vibrational modes of temperatures of nitrogen downstream of the shock are no longer defined by the same value. We are all used to, saying the temperature of this water or air is one value, but actually in this case it becomes three different one related to rotation, translation, and vibration. On these various modes of equilibrate or length scale comparable to the characteristic length scales of the flow. In hypersonic conditions, the shock layer, the region between the shock wave and the vehicle surface, must be just maybe just millimeters or even centimeters thick. So here is an example which I have taken from a paper by Mrs. Yvette Levia from Physics Today, published in 2017. What you see here is temperature. T suffix Tr is translation temperature, and that equilibrates somewhere close to here, around half a millimeter, whereas vibration temperature equilibrates, meaning that it flattens out somewhere at 1.5 centimeter, 1.5 to 2 millimeters. So each one of them is equilibrating at different. So we don't have a single definition what the temperature is of that gas at that point of time. So what really happens is that the ratio of kinetic energy to internal energy increases as the Mach number squared. In bounded layer, the flow is slowed down and the kinetic energy is converted to internal energy. And gas temperature, which is proportional to the kinetic energy, increases very, very rapidly. Hypersonic bound layers are high temperature regions of the flow due to viscous dissipation and very large kinetic energy. So there is a velocity jump behind the bow shock. As I said, when an re-entry vehicle hits the atmosphere, there is a bow shock and there is a velocity jump. And normally, behind any bow shock, we will find a large jump in pressure, density, and temperature. All at these temperatures, chemical reactions occur in the flow. A normal bow shock for an aircraft or a small missile in atmosphere is not that high pressure and temperature, but under the conditions of a re-entry, the temperature increase is substantial. So, for example, at temperatures above 2000 degrees Kelvin, oxygen is no longer O2, it dissociates. When it dissociates, it soaks up a lot of energy from the flow, from the surroundings. Similarly, nitrogen dissociates at 4000 degrees. And nitric oxide will form and begin to ionize. Above 9000 degrees, all atoms will ionize. There are no longer molecules and atoms. Everything is ionized. So hypersonic flows are also chemically reacting flows, and these chemical reactions change the flow field properties and affect the aerodynamic surface heating. So predicting the surface heating is not a straightforward heat transfer problem. It also now involves reacting flows. So as temperatures rise, thermodynamic properties, meaning specific heat, gamma, enthalpy, are nonlinear functions of temperature. Translational, vibrational, rotation modes do not equilibrate at the same time as mentioned earlier. So what T to use to compute these thermodynamic properties becomes a challenge. Chemical reactions kick in and new species are formed, getting mixture properties, diffusivities, etc., are also a challenge. And these add to the number of PDEs to be solved. Normally, when you do an Navier-Stokes equation, you have three equations for momentum, one for energy, and one for density. Now, once the chemical reactions happen, different species are there, so you need to have multiple equations. So, number of partial differential equations increase significantly. Another thing, these chemical reactions depend on exponential of the temperature. So small change in temperature leads to a very large change in the reaction rates. So by nature, these equations are very stiff. Of course, you have now standard stiff equation solvers also available in MATLAB and other open domain software. So at temperatures above 9,000 degrees, oxygen dissociation happens and they are ionized. Once they are ionized, you also have other issues which we'll briefly touch a little later. So what are the heat transfer effects? Objects are subjected to extreme heating. Protecting men and material is a major challenge because re-entry vehicles could be just unmanned, carrying scientific experiments and instruments which are being used to measure, or also it could be astronauts coming back to Earth. And if you are not good at estimating the temperature or the heating, then it could lead to catastrophic conditions where there will be damage of the equipment or even loss of life. So estimating the heat transfer to craft is a big challenge. Radiation heat transfer dominates and different species contribute to the problem because each species has its own radiation coefficient. Tunnel measurements, like especially in the wind tunnels, have been doubtful accuracy, as we cannot replicate the high enthalpies of the in the experiments. High enthalpies because of the high velocity, high kinetic energy. That's impossible to replicate in the tunnels at present. Of course, there is a hypersonic tunnel in the Indian Institute of Science, Bangalore, where do some experiments using shock tunnels into finding out measurements on the species and everything else. Such temperatures, at high temperatures, alter the material behavior of classical materials. Aluminum alloy, CRP, CFRP, meaning carbon fiber reinforced plastics, are ruled out. Radar absorbing materials, especially used for stealth, is also ruled out. So you need to come back with different kinds of material which can absorb this kind of temperatures. A quick infographic from NASA. This is a re-entry body typically entering the blunt side first so that you create a bow shock. Most of the energy is dumped in front of the re-entry body, not on the body. That's the idea of coming blunt first. So here you can see there's a bow shock, viscous interaction, shock layer, a whole lot of phenomena happening here. And there is a separation at this. And at this point, you can see continuum breakdown, meaning that you can no longer treat the air as a continuum, which means there are several other issues. We'll talk about that a little later. And you also have what's called an ablation coating, which is a coating on the re-entry body where it sucks up the heat from the bow shock and it dissociates. When it dissociates, it actually protects the body underlying it by, you can say, some kind of sacrificing itself by dissociating. So ablation and recession is part of the thing which you have to understand. Now let's look at what happens at low density flows. Atmosphere is composed of discrete atoms and molecules. As we know, a useful approximation arises if the atmosphere is treated as a continuum. Continuum meaning like of a liquid where there are no gaps. In reality, it's not so, but it's a useful approximation under normal conditions like sea level and even up to about 10 to 20 kilometers altitude. The flow over a vehicle moving through atmosphere can then be modeled by fundamental principles of mass, momentum, and energy conservation, yielding partial differential equations, which can be handled. A lot of existing software is available, both the commercial and open domain to do that. This continuum approach, where you're treating the atmosphere as a continued fluid, is at the root of the CFD methods for solution of Navier-Stokes equation. So continuum models used in CFD have limitations in rarefied gas dynamics. There's a number, just like Mach number, Reynolds number, there's another number defined here called Knudsen number, which is the ratio between mean free path and the typical length scale of whatever the aircraft or a rocket or a missile you are looking, any physical length scale. This is a good approximation for rarefaction. As the Knudsen number increases, the non-continuum particulate behavior of the gas becomes more important. You can no longer treat it as a continuum. You have to treat them as a bunch of particles independently coming and impacting on the surface of the physical surface. Numerical models hoping to simulate such rarefied conditions must be able to capture this complex physics. Now let's take a look at what I mean by saying low density flows. So applicable, which are applicable at high altitudes. At air at low altitudes, 11 to 15 kilometers, where generally most commercial aircraft fly. Some of the combat aircraft can fly even at higher, about 20, 22 kilometers, not much more than that. So this is very well modeled by a continuum medium. However, at 100 kilometers, the continuum hypothesis is no longer valid. The individual molecular impacts on the surface become important. So just give you an idea, there's a small table here. So at sea level, the mean free path is around zero point 0.1 micrometer. At 100 kilometers, it's 16 centimeters, and at 300 kilometers, it's 20 kilometers. What it means at 300 kilometers, an air molecule has to travel on an average 20 kilometers before it meets another air molecule. So obviously, it's no longer continuum. Air, in this case, must be treated as a collection of distinct particles, molecules, atoms, ions, all of which can be widely separated from one another, as I've seen in this thing. All our aerodynamic concepts, equations, results that rely on continuum hypothesis break down. Popular CFD codes like Fluent, CFD++, star, etc., are not applicable as all are based on continuum hypothesis. So aerodynamics now should be based on kinetic theory of gases, going back to the original kinetic theory, which are applicable to low density. Again, continuum is when Knudsen number is less than, very much less than 1. Continuum hypothesis holds, which holds up to over 20 kilometers in the atmospheric conditions, or even in the sea, underwater, and all that. It is a continuum mechanism. Free molecule flow, low density flow, when Knudsen number is greater than 10. So in such cases, we need to use a different kind of software. One such option is called Direct Simulation Monte Carlo, or DSMC, which has been popularly used now. In free molecule flow, the body surface feels only a small number of distinct molecular impacts. Shock waves become very, very thick. Basically, they lose their identity. They are no longer thin. Cl, Cd, Cm coefficients and surface heat transfer coefficients become strong functions of Knudsen number, in addition to Mach number and Reynolds number. A realistic body flying at high Mach number and Knudsen number can vary along with the length of the body. So Knudsen number is no longer one number for a realistic body. Typically, for example, a space shuttle which takes off from the atmospheric and sea level, then it is no longer free molecule flow. Once it goes into space, you have free molecular flow. Once it enters the atmosphere, again you have hypersonic conditions and all that thing. So it varies along the length of the body. So there are some experiments which have been done, and this what figure shows in the y-axis inverse density thickness, which basically is equivalent to reciprocal of the shock thickness. So higher the number, which means the shock is predicted shock thickness is lower, smaller. On the x-axis, you see the Mach number. As you can see, the experiments predict a much, much thicker shock than what Navier-Stokes shows. So this is a major area where there is a error which is seen. That so look at also the temperature jump across the shock waves. So what you see here is again an x-axis Mach number varying from 0, which is incompressible, to about 24, and the temperature jump across the shock waves. Perfect gas, perfect air predicts a very, very high temperature jump, whereas in reality it doesn't happen. Remember the example one where it predicted 40,000 degrees Kelvin. In reality, it doesn't go that high. Basically, what happens is that Mach number increases, energy goes into vibrational rotational modes, hence increase in T flattens out as my Mach increases. It's no longer going very high as in this case. This is basically a log scale, log scale in y direction. However, there is no difference in pressure increase, whether we take perfect gas or air in thermodynamic equilibrium. Pressure increase is about the same. There's no change in that. A temperature jump, as I mentioned earlier, calorifically perfect gas, what we normally treat under atmospheric conditions. This is how it goes. For example, a Mach number of 10, temperature increases 20 times, meaning if we are at sea level 300 degrees Kelvin, so 20 times that will be the predicted temperature, whereas in reality, it is not. So as you go higher and higher altitude, let's say 80,000 feet or 120,000 feet, equilibrium air, then you see that there is a distinct reduction or a lower prediction of temperature. So it's just not the temperature and other prediction. There are more important issues like aerodynamic coefficients. All of us are, familiar with this moment coefficient Cm versus alpha, or sometimes Cm versus Cl prediction, which is very, very useful in terms of stability estimations. It has been found that the standard ways of predicting this CMCL has been found wanting. Results in under or overestimation of this control surface lead to control surface deflections. For example, if I have predicted this 20 degrees deflection for perfect gas, in reality, it won't be that. It has been reported that issues of this caused a scare in the first re-entry of space shuttle. 11 degrees was the estimated deflection of the body flap. An astronaut had to use 16 degrees, which was the maximum available. So luckily for them, they could survive. If it had been more, if that 16 degrees was not available in the flap deflection, then it would have been a catastrophic condition. Just interesting. This is the body flap I'm referring to, which had to be deflected at the maximum, and there was a hard stop. It could not go beyond 16 degrees. Luckily for them, it was okay, and they survived. Now let's look at the early efforts. Hypersonic simulation is not something new. As usual, in most of the things, Isaac Newton had a hand in estimating this. Early in 1700s, he predicted, he assumed that the air molecules travel and that individual molecules impact the surface. This is the local body surface. So he assumed that the tangential thing doesn't contribute to anything, only normal velocities contribute to it. So he derived an expression for pressure coefficient Cp, Ps minus P infinity by dynamic pressure, half rho infinity. So this is a standard thing which we all use in aeronautics. And he came with this equation saying that it is simply 2 times sine square theta b. Theta b being the angle the surface is making with the horizontal. So notice here, it doesn't depend on the Mach number at all. So for any body, we just need to find the local slope and get the Cp. That's it. It doesn't depend on Mach number. So it looked very, very simple. Then people did a lot of research and came back with experiments and all that, and then found that what Newton had predicted as 2 is actually 1.85. As you can see, it's not really a big deal change. And he got pretty good at that time, 1700s with no calculators. Forget computers, even calculators were not there. He still was able to get pretty close to it. Here's a comparison pressure coefficient. Experiments, Newtonian theory is the solid line. It's little over predicting. And modified Newtonian theory is this. It's a pretty good agreement considering that it was done in the 18th centuries or maybe a little earlier than that. With no modern equipment, he still was able to do this. Sorry. However, the issue is not covered in this small presentation. Challenges in propulsion, especially scramjet, you need to develop. This involves supersonic combustion. What actually happens now, most of us have heard about this BrahMos missile, which can travel at Mach 3. So it uses initially a rocket to accelerate it to high velocities, supersonic conditions. Then it switches to ramjet, which can operate up to Mach 3. Anything higher than Mach 3, ramjets do not work well. You need something called supersonic ramjet. And this needs supersonic combustion. It's like lighting a matchstick in front of in a tornado. So this is something which is a very, very big challenge. Recently, India has managed to do some experiments successfully. So hopefully we'll have an hypersonic missile quite soon. Other issues are electromagnetic interference. Because all the surrounding area is breaking down into ionization and everything else, they will interact with the electromagnet communication and navigation systems. I have not covered experimental methods because personally I have not worked in experimental methods. But like to mention here, there is a high enthalpy hypersonic wind tunnel in the Indian Institute of Science. So if you do happen to get into the Indian Institute of Science, either for masters or PhD, you can register in this domain and then do research in that. Theoretical methods for low density flows is another issue. Kinetic models, these have a large impact on heat transfer. These are the things which I have not covered. Some of the references are here. I'd like to point out one key part here. There is a report called CCD Report 2018-1, Simulation of Non-Equilibrium Hypersonic Boundary Equations using Navier-Stokes equation. They have done this comparison over a variety of bodies, and a lot of data is available for anybody to who wants to replicate it and compare it with that. There is also a open domain software called SU2. It's NEMO version, non-equilibrium model version 8.1 is an open source software, Stanford University software code, which has been used extensively by some of the students from the Ramaya University of Applied Sciences. That brings to the end of this presentation. Thank you for listening. And if possible, share this video with your friends and others. This is a non-commercial effort. It's purely for educational purposes. Thank you.